Today we are going to review and practice for CFA number 6. The first question asks you to graph the absolute value function -2 times the absolute value of x minus 3. A couple things to ask yourself on these. Is it reflected over the x-axis? That would be denoted by a negative in the front, which in this case we do have a negative in the front. So we know there is an x-axis reflection. And although it doesn't ask you for these things, it helps you visualize the graph as you are graphing it on the axis. Also, since the absolute value is essentially the combination of two pieces of a line, you want to know what the slopes of those lines are going to be. In this case, because we have a 2 in front of the absolute value sign, that represents our rate of change on either side. I'm just going to use it, m for slope is going to be plus or minus 2 from the vertex. And then did we go right or left? We did not, because there's nothing added or subtracted on the inside of the absolute value symbol. And did we go up or down? Which, yes, we did, because of the -3. The -3 tells us that we go down 3. So if you remember from the parent function of the absolute value graph, usually it starts at 0, 0 with a slope of 1. So it's going to go up 1 over 1, up 1 over 1 on each side. You draw enough points so that you can get a good graph. So the parent function y equals absolute value of x looks like this. And I'm going to draw that line all over again. I'm horrible at drawing straight lines. All right, so there's our parent function y equals the absolute value of x. All right, but this one has been reflected over the x-axis. It has now a rate of change of 2 instead of 1, and it's been shifted down 3. So that vertex that was at 0, 0 is now at 0, -3. And then from that vertex, since it is reflected over the x-axis, we know it's flipped down. So we're, instead of going up and over to get our points for our absolute value graph, now we're going to go down and over. In this case, we're going to go down and over 2, because the average rate of our lines is plus or minus 2. So I'm going to go down 2 over 1 on each side. That's enough to get us a decent. And so here is my transformed absolute value function. The second problem is asking you to find the sum of the first 9 terms of 3 different geometric sequences. If you recall, the formula to calculate the sum of a geometric sequence is the sum for any given amount of terms. In this case, our n is going to be 9. We want the sum of 9 terms equals our first term times 1 minus the ratio raised to the n, and that's all over 1 minus r. So really there's 3 things that we need to know for these sequences. We need to know our first term, we need to know our ratio, and we need to know our n. In this case, for all 3 of them, n is going to be 9, because we want the sum of the first 9 terms of the sequences. So let's take a look at 2a. If you look at 2a, to go from 48 to 24, 24 to 12, and from 12 to 6, and so on, we have to remember it's all about what you're multiplying by to get each term in the sequence. To go from 48 to 24, I have to multiply by a half. To go from 24 to 12, I have to multiply by a half, and so forth and so on. So the ratio for 2a is 1/2. The first term, which we also need, is 48. And n for all 3 of these is going to be 9, because we want the sum of the first 9 terms of the sequence. So if we put that all into the equation for 2a, we get s sub 9 equals 48, which is our first term, times 1 minus the ratio. The ratio is 1/2, and that's being raised to the n. It is 9. And then that's all over 1 minus r, so 1 minus 1/2. If you're really good about doing this in one step, just make sure you're very careful about parentheses. Otherwise, do each of the steps individually, remembering your order of operations. So remember, parentheses comes first, so you would do the inside of this first, then multiply it by 48, and then divide by the 1 minus r. If you put this all in your calculator correctly, you should get this, that the sum is equal to 95.8. 2b is a little bit different in the sense that instead of our numbers going down as they were in 2a, now our numbers are going up. So we have to ask ourselves, what do I need to multiply 1 by to get 4? Well, I'm pretty sure I have to multiply it by 4. To go from 4 to 16, I have to multiply it by 4 as well. So our ratio is going to be 4 for this example. We're multiplying by 4 every time to get each term in the sequence. So we know our ratio is 4. Our first term in this sequence is 1, and remember, n is still 9 because we're finding the sum of the first 9 terms in the sequence. So plugging it into the formula for this example, first term is 1. So it's 1 minus the ratio, which is 4 raised to the 9, and that's all over, all over 1 minus the ratio. The ratio again is 4. If you put that all in your calculator correctly, you should get that this is 87,381. And lastly, this one is interesting. We didn't do many of these in class. Notice that the terms in the sequence go from positive to negative to positive to negative. They alternate signs. The only way for that to happen is if your ratio is negative, because a negative times a positive is a negative. 2 negatives give me a positive. So what it's going to do is going to oscillate back and forth between positive and negative. So first figure out what the ratio has to be to get essentially the absolute values of these numbers, and then it's going to be negative in order to get that alternating sign. So let's take a look real quick. To go from 1 to -3, I have to multiply by -3. To go from -3 to +9, I also have to multiply by -3 because -3 times -3 is +9, and it keeps following that pattern. So our ratio for this one is -3. And just remember, if it's oscillating signs like that, the ratio will always be negative. So our ratio is -3. Our first term is 1. And our n, again, is still 9. So plugging into the formula, we've got that the sum of the first 9 terms of this sequence is the first term, which is 1, times 1 minus the ratio raised to the n. Now be careful with parentheses here because you're taking -3, you're raising it to the 9th, but you're taking that and subtracting it from 1. So you have to do those exponents before you do the subtraction, and make sure you put that -3 in parentheses when you're putting it in your calculator. And then that's all divided by 1 minus a -3. And again, be careful with these signs right here because 2 negatives become a positive. All right, when you put it into the calculator, being really careful with your parentheses and with your signs, you should get that the sum of the first 9 terms of this sequence is 4,921.75. Question number 3 gives you the parent function of absolute value of x and wants to know what the new equation for the transformed function would be if it's been shifted right 4, up 1, and reflected over the x-axis. So let's talk about first this shifted right 4. If it's shifted right 4, that means there should be something subtracted inside of the absolute value sign. Remember, it's opposite what you would expect on the inside. So if I want to go right, I should have x minus something. If I wanted to go left, I'd have x plus something. Since I want to go right 4, I should have x minus 4 inside of the absolute brackets. And if you're really smart and take a look at your choices before you keep going, what you'll notice, and I don't know if this was our intention, but what you'll notice is there's only one of these choices that has x minus 4 on the inside, and that is choice number C. But let's pretend maybe you didn't look at the choices and you didn't notice that. Let's then move to the fact that it has to go up 1. Up or down is taken care of by whether you're adding or subtracting something off the end of the function. So since I'm going up 1, that means I should have a plus 1 on the end. And again, if you look at these choices, this is the only one that has plus 1 on the end. And then lastly, we want it reflected over the x-axis. For that to happen, there should be a negative in the front. There are actually 3, A, C, and D, that have a negative in the front, but only C fits all 3 characteristics. All right, we are solving a base 3 log equation. Remember, if you are solving a log or an exponential equation, you're always going to end up converting to its inverse form in order to solve. So since this is a log equation, I know I'm going to convert it into an exponential eventually to solve. The key for any of these problems, any of these solving equations, is to get either the log or the exponential by itself before you convert. So in this case, the log is already by itself. There's nothing I need to move to the other side to isolate it, so I can go ahead and convert. So start with your base, as we've done in class. In this case, the base of the log should be the base of your exponent. So the base of my exponent is 3. Go in this case, go towards the equal sign always. So we're going in a counterclockwise motion, starting with base 3. It's going to be log base 3 of 2 equals 2x plus 5. So everything you come across as you're going counterclockwise is how you write it in the form. So once again, that's base 3 raised to the second equals 2x plus 5. So if we write that in the correct form, we've got 3 to the second equals 2x plus 5. We can change or simplify 3 to the second as 9 equals 2x plus 5. Now it's just a matter of solving a linear equation. So we're going to subtract 5 from both sides. Oops. That gives me 4 equals 2x, last step. Divide by 2 on both sides. So we get that x equals 2. All right, now we've got the opposite case. Now we're starting with an exponential and we're solving. So if I'm starting with an exponential, I know eventually I'm going to convert it into a log, unless I can use one of those special properties that we learned, which in this case we can. Remember, if we can make the bases of our exponential the same on both sides, we can, in a sense, disregard the bases and just equate the exponents together. So if there's some way that I can rewrite 1 over 16 to have a base of 4, then I can use that property. And it just so happens that I can. So I'm going to leave 4 to the 5x plus 8 as it is. There's nothing I can do with that. But I think I can rewrite 1 over 16. But remember, if the 16 is on the bottom, that means the exponent must have been negative. So 1 over 16 can be rewritten as 4 to the negative second. Now we have a situation which is exactly what we want. The bases of our exponentials are the same. If we're saying these things are equal and the bases are already equal, then all we have to do is set the exponents equal to each other. So we can say that 5x plus 8 equals negative 2. And again, it's just a matter of moving things around and solving for x. So I'm going to subtract 8 first. That gives me 5x equals negative 10. Last step is to divide by 5. And that gives me x is equal to negative 2. Question 6 is a 3-part question. It is not multiple choice. So in this question, you're asked to determine how many solutions each system has. Remember, system is a set of either 2 or more equations. So we've got 3 systems here. We want to see how many solutions there are to the system. Graphically, remember, solutions are determined by where these equations in the system intersect. Now, if you take a look at these equations, some of these are pretty intense. So we do not expect you to graph these by hand. What we do expect you to do is use your technology, use Desmos, graph the system, look at how many times each of these equations or intersect each other to determine how many solutions the system has. So what I went ahead and did, just to save time, is I took each of these systems and I went ahead and put them in Desmos. So if we take a look at the first system, which is looking at f of x equals the absolute value of x minus 2 plus 3, and g of x equals negative 2x squared plus x plus 3. I went ahead and graphed those. I actually graphed all 6. I'll turn them on as we get to them. So if you go to the first system, I'll turn those on. So there is the equation of our first system. If you notice, if you look at both of them, there is nowhere that they intersect. So this would be an example of no solution. There is no value of x that makes both of these equations true. So when we go back, we're going to say that this system only has, or not only, it has 0 solutions. So we're going to say no solutions. if you say 0, that is also fine because it technically asks how many. So yes, that is the same as saying 0 solutions. All right, second system is f of x equals ln of x plus 3 and g of x equals x squared times 1/4 of x plus 1. So again, we're going to go back to Desmos. You would be doing this individually on your own, but we're going to go back to Desmos. I'm going to turn these off, turn on the next two equations in our system. And if you look here, you can zoom out a little if you want, but if you look here, they cross in exactly 2 places. So this system has 2 equations, or excuse me, 2 solutions. So we've got 2 solutions here. Okay, and then the last system is a rational function combined with a square root function. So again, we're going to go back. I'm going to turn these off. I'm going to turn those 2 systems on. And this one, you got to be careful because you have to sort of move it and zoom out a little bit in order to see everything. One of them is a rational, so there's your 2 pieces of the rational function. This one is the square root, and remember it's a one-sided graph. These two functions in the system intersect in exactly one place, which is right there. All right, so this is an example of a system that has exactly one solution. So basically, you've been given an example of 3 systems that each have either 0, 1, or 2 solutions. Just remember, you're graphing them in Desmos and looking for how many times the graphs intersect each other. All right, our favorite question where we have to solve for a variable when there's a lot of variables. That's okay. We're going to get through it. Remember, the objective when you solve for anything is just to get that thing, in this case, p, all by itself. So everything gets moved to the other side. Now, in this case, p is part of an exponent. So basically, it's part of an exponential. In order to convert an exponential so that we can solve for anything in the exponent position, we have to convert it to a log. So eventually that's what we're going to do. But remember what I said earlier on. If we want to solve an exponential and convert it to a log, we have to isolate that exponential first. So this has to be isolated first before we can convert, which means I need to move that 4 to the other side. Since 4 is being multiplied by n to the pq, I'm going to divide both sides by 4 first. That's my very first step. Rewriting that, I get 16m over 4 equals n to the p cubed. But notice that 16 is divisible by 4. I'm going to go ahead and change that and simplify it so we're not dealing with a fraction. 16m divided by 4 is the same as 4m. And then that equals n to the p cubed. Now we've got this exponential all by itself. Now I can convert it. I have to in order to drop that exponent down so I can solve for p. So remember, you always, when we convert, we go towards the equal sign starting with the base. All right, the base of my log should be n. All right, and then we're going to go towards the equal sign. Everywhere I hit as I go around to the exponent is how I write it. So it's going to be log base n of 4m equals pq. Again, that's log base n of 4m equals pq. Now we're almost done. We almost can solve for q, and I know that's a weird q. I promise you it's a q. All right, the last step we need to do is to move that q. That's in the way of solving for p. That's p times q. So to move that q, I'm going to divide both sides by q. And now I've got p by itself. So we can say now that p is equal to log base n of 4m all over q. All right, moving on to systems. We know it's a system of, in this case, inequalities, because it's going to give us some words that clue us into that we're using inequalities. So let's take a look and see what it says. It says you are buying crumble cookies for your class. Lucky class. There are 2 new flavors this week. You want to get at least 5 of both flavors. All right, that's really important, so I want to underline that. We need at least 5 of both flavors, but we do not want to get any more than 24 cookies. So another constraint is that we want to have no more than 24 cookies. So we've got 3 constraints here. It looks like 2, but remember there's 2 flavors of cookies. We're going to let F be the first flavor. All right, so I'm just going to write this out over here. We're going to let F be the first flavor. We're going to let G be the second flavor. Now it says that we want at least 5 of both flavors. So if we're letting F be the first flavor, we want at least 5 of F. So we can rewrite that as F must be greater than or equal to 5. We also want 5 of G, of the second flavor. So we can also say that G must be greater than or equal to 5. Now our last constraint is that we do not want to buy more than 24 cookies. In other words, if I add both flavors, the amount of both flavors that I get together, I don't want to have bought more than 24 cookies. So I can say that using the constraint that F plus G must be less than or equal to 24. So if we take a look at our choices, the correct answer should be A. All right, solving a log equation. Remember, if we start with a log, we're going to end with an exponential eventually. Also, notice that I've got 2 logs on one side. If I am solving and I have more than 1 log on a side, I have to condense it first. Also, notice here that the bases of the logs are not written, so we know by now that by default that is a base 10 log if that base is not written. So I'm going to go ahead and put it there because we're going to need it when we write the exponential. Also, note that this is a difference of 2 logs that have the same base. And remember, if it is a difference, that implies the quotient property. Anything that is positive, any term that's positive goes on the top, any term that's negative goes on the bottom. So this term right here is positive, so the x plus 1 is going to be on top of the quotient in the numerator. The negative log base 10 of 5, or the log base 10 of 5 is negative. That means the 5 is going to be in the denominator of our quotient. So if we rewrite the left-hand side of this equation, we've got log base 10 of x plus 1 on the top, 5 on the bottom of our quotient, and that still equals 1. Now, if we did not have the log by itself, we'd have to move things before we can convert. But we've already isolated the log, so now we can convert so that we can get rid of that log that's blocking the x plus 1 over 5 so we can eventually solve for x. All right, remember, start with your base. No matter which type of equation you have, go towards the equal sign. All right, my base is 10. So when I write the exponential, I'm going to say 10 raised to the 1 equals x plus 1 over 5. Once again, that's 10 raised to the 1 equals x plus 1 over 5. 10 to the 1 is just 10. I could have wrote that, but I just wanted you to see where that 1 ended up going once we converted. So this actually is just 10 equals x plus 1 over 5. I need to move that 5 from the denominator to the other side so that I can solve for x. So I'm going to multiply by 5 on both sides. That's going to cancel out the 5s on the right. That's going to give me 50 equals x plus 1. And the very last step is to subtract 1 from both sides. And that gives me that x equals 49. All right, we've got another system of equations here, in this case, system of inequalities. We've got some constraints we need to figure out. We need to graph those constraints and then figure out where our feasible region is. That's where we have our solutions to our system. So let's take a look at our constraints really quick. We're making cakes and pies. We're going to make cakes X. We're going to make pies Y. And we're making cakes and pies for the bake sale. We want at least 3 cakes and no more than 8 pies. So let's go ahead and take care of those constraints really fast. If we want to make X cake and we want at least 3 cakes, we are going to say that X must be greater than or equal to 3. Now, we want no more than 8 pies. All right, so basically, as far as pies goes, we want 8 or less. So we're making y be pies, so we need y to be less than or equal to 8. And then finally, we have a time constraint with regards to our time. All right, a cake takes 2 hours to make, and a pie takes 3 hours to make. Altogether, we do not want to spend any more than 12 hours making cakes and pies. So if I combine the amount of hours I spend making a cake, so 2 hours per every cake, so 2x, and add that to the amount of hours I spend making pies, which would be 3y, 3 hours for every pie I make. We're making y pies. The sum of those hours we do not want to be any more than 12, so we're going to say that that has to be less than or equal to 12. Now, in order to figure out which of these possible combinations of cakes and pies, remember the x-coordinate would be cakes, the y-coordinate would be pies, we first have to graph these inequalities in the first quadrant. Now, technically, one thing that we did not write here, but is always true for most of the ones that we're going to be doing in this class, is that x is also has to be greater than or equal to 0, as do the y's. That is sort of implied here because you only have the first quadrant to graph in. But in general, you want your x's to be positive as well as your y's when you're doing these application questions. So let's go ahead and graph x is greater than or equal to 3. That is a vertical line. So we should have a vertical line at 3. Now, I'm going to go ahead and label or the scale on my graph so we know exactly what we're doing here. You have enough room to go up by 1. All right, so I'm going to make this 1, 2, 3, 4, 5, 7, 9, and then this would be 11, which would make the last one 12. I'm going to do the same thing here. We're going to say this is 1, 3, 5, 7, 9, 11, and the last one will be 12. All right, we want x to be greater than or equal to 3. This is a vertical line, so we should have a vertical line that crosses at 3. All right, so I'm going to draw my vertical line at 3. Now, I'm going to use arrows to show shading. Actually, you know what? I have some colors. I'm not going to do that. So we want x is greater than or equal to 3. So we're going to shade this one. We'll do, I'm filling some magenta. So if everything greater than or equal to 3 is to the right of that vertical line. Okay, so that takes care of the first constraint. Second constraint is that y must be less than or equal to 8. That is a horizontal line that crosses at 8. So now I'm going to draw a horizontal line crossing at 8. All right. Now this time I want these values to be less than or equal to 8. So you're going to want to shade down. All right. And lastly, now we have the fun one. We have 2x plus 3y has to be less than or equal to 12. In order to graph a slanted line, you want to find the x and y intercepts and then connect them. So if I want to find the x-intercept for this, I'm going to let y equal 0 and solve for x. So again, we're going to find the x-intercept first. You could do the y-intercept first. I'm going to find x. So we're going to set y equal to 0, which means that 2x must be less than or equal to 12, which if I divide it by 2 on both sides, that tells me x must be less than or equal to 6. So we should have an x-intercept at 6. So that slanted line is going to cross right there. The y-intercept you're going to get by taking the same equation and setting x equal to 0. So now 3y must be less than or equal to 12. Divide by 3, you get y, not x, y must be less than or equal to 4. So now on the y-axis, we have another dot here. That's where it crosses the y. And if you connect those two, there is your line. Now we want it to be less than or equal to this value. All right, so we want to shade below. So let's use this color so it's easy to see. So we want to shade below that line. Now remember, we're looking for all 3 of those colors intersect, and there is only a very small area where that happens, and that is this triangle right here. All right, so right here is the very small area that represents our feasible reason, and inside this area are the only combination of x's and y's that will make these 3 equations true. So if we look at our choices, let's do 2, 4. That's 2 cakes, 4 pies. So if I go over 2 and up 4, that doesn't put me in that triangle. Let's try B, over 3 up 2. over 3 up 2. Now, it looks like it's not in the triangle, but actually is. Remember, all of these inequalities are equal to, so they can land on the line as well as inside of the shaded region. 3, 2 is actually on the line. So let me see if I can get a better color here. Let's the color I haven't used. All right, let's do orange. No, that's too easy. Let's do blue. All right, so 3, 2 is right there. That is actually in the feasible region because it is on all of the lines that connect that vertex of that triangle. So it can either be inside the shaded region or it could be on the shaded region, on the lines that represent it in order to be a solution. So it looks like B is the answer, but let's just verify. Let's just double check them all just to be on the safe side. So I'm going to go ahead and pretty much say that it's B, but let's look at C. C is 4, 4. If I go over to 4 and up 4, that's not in the triangle. Let's try 5, 2. Over 5, up 2, also not in the feasible region. So as we expected, the answer is B. We want a possible combination is 3 cakes and 2 pies. All right, graphing piecewise functions. A couple of things to remember when you're graphing these. If there's no equal to as part of the domain constraint, then the circle should be open. If there is an equal to, that circle should be closed. So let's take a look at the first piece, which is x squared. So it's a parabola. And we want that parabola between, or for all values where x is less than 2. All right, now, I like to plug in points, specifically the points that relate to the constraints, to see what part of the graph that I want to see. All right, so let's just do x equals 2 for x squared. So when we put in 2 for x squared, so if I do f of 2 for this first piece, that's going to be 2 squared, which is 4. All right, so on this first function, I'll just call 1. We have a open circle because there's no equal to there. We have an open circle at the point 2, 4. All right, so at 2, 4, I'm going to put an open circle. All right, now we don't want any graph to the right of that because this is our rightmost point. We want the graph now that is to the left because of this less than sign. We want the graph to the left of 2. So now I'm going to plug in some more points to get some more another piece of the graph so I can see what it's doing to the left of 2. So now I'm going to do f of 1. So I've got f of 1 in the same piece still. So I'm going to that's going to be 1 squared, which is 1. So we've got a point at 1, 1. So I'm going to go over 1, up 1. I'm going to do f of 0 too because I'm trying to see what part of that U shape that I've got. So f of 0 is 0 squared. 0 squared is just 0. So we've got a point at 0, 0. So we've got a point here. Now, if you keep going, keep plugging in points because you do want to get a good bit of the curve because basically you're seeing all this quadratic except the little piece to the right. It turns out you're also going to have a point here. You're also going to have a point here because remember, parabola is symmetric. At -3, you have 5, 6, 7, 8. You also have a point at 9. So if I were to draw this, there is my piece of that parabola that is to the left of 2. And again, I've got an open circle on 2 because there's no equal to underneath it. Now, this one's interesting. The second one is actually a point. It's not a horizontal line because the only value that makes this true is when it is 2. So basically, this is saying at x equals 2, the value is 6. All right, so at 2, 6, so over 2, up 6. So I'm going to do this as a different function. You just have a dot. So this is over 2 up 4, 5, 6. So you have a dot right there, and that dot represents this second piece. All right, now if this had been an inequality, like if it had said 6 is between 2 and 5, then you would have a horizontal line. But because it's just one value where this is true, that piece is just a point, and it is closed because that says equal to. All right, the last piece is 10 minus x between 2 and 6. So I'm going to do the same thing. I'm going to use my constraints to tell me what to plug in. So I want to plug in 2 to see what my left point of my segment is, and I want to plug in 6 to see what the right point of my segment is. So let's plug in 2 first. So now I'm going to do a different color because we're plugging into a different equation. So I'm going to plug in 2 into this equation right here. So that's going to be 10 minus 2. That gives me 8. So I have a point at 2, 8. So I'm going to go over 2, up 8. That one should be open because there's no equal to right there. I'm also going to find f of 6 because I want the other side of my segment. So that's going to be 10 minus 6, which is 4. So I have another point at 6, 4. All right, so I'm going to go over 6. So 1, 2, 3, 4, 5, 6, up 4 puts me here. It is closed because there's an equal to there. And then I just connect those points. So there is my piecewise function represented by 3 pieces. First piece was I made in purple. Second piece was that point, and the last piece was that segment represented in aqua. All right, number 12, we have one scenario or one setup with 2 different scenarios. In both of them, we're investing $1,500 in a 5-year CD. So since it says 5 years, that means that T must be 5 because it expires after 5 years. It gains interest at a rate of 4.5%. So our rate is equal to 0.045 as a decimal. Determine how much money you will have at the end of its term if it is blank. So we have 2 possibilities. What is it when we compound monthly? What is it when we compound continuously? Remember, these equations are not given to you. If it says compounded monthly, in other words, it's like monthly, daily, yearly, something like that. It says compounding, but not continuously. You're going to be using the following equation. Your final value is equal to your initial value times 1 plus the rate divided by n, all raised to the n times t. All right, in this case, our initial value was 1,500. All right, times 1 plus our rate was 0.045 divided by n. Now, since it's monthly, n is 12. So we're dividing 0.045 by 12, and that's being raised to the 12 times t, and we said t was 5 because it's a 5-year CD. Now, I'm not going to go through the calculations, but remember, be careful. If you're doing this in one step, you want to make sure you put this part in parentheses inside there or it will not do it correctly. I'm always overzealous with my parentheses just to be on the safe side, but if you put it in correctly, you should get that your final value, if it's compounded monthly, is $1,877.69. Now, the second scenario is okay, same setup. We still have 1,500, still 4.5%. But what is the value if we do it continuously? So if it uses the word continuously, not monthly, not daily, not yearly, still compounded, but continuously, you're using the PERT formula, which is A, final value equals initial, which were same as principal. So P times E raised to the RT. Remember, E is not a variable. It is a number in your calculator. Our initial value is still 1,500. Times E raised to the RT. R is 0.045. T is 5. All right, plugging that into your calculator, you should get the final value is $1,878.48. Now, if you compare the two, obviously there's not that huge of an advantage between taking this investment at the same interest rate and compounding monthly versus continuously. Continuously gets you about an extra $1, which I guess is better than nothing, but there's not a huge difference. Just remember the formulas for each setup and the keywords that tell you which formula to use. Number 13 asks you to describe the end behavior of the graph below. All right, notice first of all, this is a log graph. I know this because visually, if you look at it, it is flattening out vertically. In other words, it has a vertical asymptote. That asymptote is at x equals 1. Also remember that for log functions, when you're approaching on either the right or the left side, one of them is constrained because of this vertical asymptote. So let's take a look at the end behaviors. The first one says, as I approach infinity, so as I go to the right, my my values of my function, my f of x goes down to negative. Well, as I go right, they do go down to negative, but the problem here is this. All right, I cannot approach infinity when I go to the right because of this vertical asymptote that is blocking me from crossing. But as I can I can approach the asymptote as I go to the right. So instead of saying as x approaches infinity, I'm going to say as x approaches 1, then my y as my function goes down to negative infinity, which would give you choice B. All right, let's just look in C and D just to make sure you understand why those are not correct. C says as you go towards negative infinity, which means, as you're going along your graph towards the left, I'm approaching negative infinity. It's saying my y's are going to go down to negative. As I go left to negative, my y's are not going down. They're actually going up to positive. So this part right here makes that statement false. And the last one says as I approach negative. So again, as I go left, my y's are approaching 3. Now it does look sort of like it's flattening out there. However, that is not a horizontal asymptote. All right. There are no horizontal asymptotes for log functions, only vertical. So as I go left, even though it looks like it's flattening out and approaching 3, it is actually approaching positive infinity. So this is the part that is incorrect on that statement. So as we just said, the correct answer for this question is B. As I approach 1 on the right, my y's go down to negative infinity. All right, almost done. Number 14, we want to take this piecewise function, which is actually a step function. You can see it sort of looks like steps as you go along from left to right. We want to write the equation of this step function. Now, step functions are just another type of piecewise function. So remember, piecewise functions always start with f of x equals a single brace, and then we're going to fill in our equations with the number of pieces we have. So in this case, we have 1, 2, 3, 4 steps. So we should have 4 equations in our piecewise function, and each of those have constraints based on how long they are horizontally. So we always go left to right. So let's start with this blue piece right here. That is a horizontal segment that crosses at 4. So this is I'll try to color code here. So the blue, and I don't have blue, let's use purple. All right, so the first segment has a value of 4. If my x's go from 0 to 1. Now, on the 0 for the compound inequality, it should be open, so there should not be an equal to. On the 1 side, it should be closed. So when I'm writing the compound inequality, make sure those symbols are correct with respect to whether it's an open circle or a closed circle. So for this one, my horizontal segment lies between 0 and 1. Notice that I put the equal to on the right because that's where the closed dot was on the right side of the segment. And that's going to be true for all of these. So rather than restate that over and over again, for all of these steps right here, the right number on my inequality should be the equal to because they're all closed. The left number should be the one that's not equal to. All right, my second segment is a horizontal segment crossing at 6. So its value is 6 if x is between 1 and 2. All right. Next segment is a horizontal segment that would cross at 8. We'll make this one a little different. So we'll say orange. All right. And that happens if my x's are between 2 and 3. And then lastly, this last longer segment has a value if it were to cross of 10 if x is between 3 and 12. And lastly, just one last comment as a reminder, notice that all the inequalities next to the lower bounds do not have an equal to. That's because all the left circles are open. All the right circles are closed. That's why all the upper bounds have the equal to underneath them. All right, we are headed towards the finish line. Last question. Which statement is true for the following exponential function? So before we get started, remember that exponential functions have a horizontal asymptote, you can see that it's flattening out horizontally right here. That's at y equals 2. Remember, horizontal asymptotes constrain your range. They do not constrain your domain. Also remember that if you're talking about an exponential function, the domain is always all real numbers because of the double-sided arrows. This arrow on the left goes to negative. This arrow on the right eventually goes to positive infinity on the x-axis. So eventually this graph will cover the entire x-axis. The domain is not constrained at all. The range, however, is, because this graph cannot cross this horizontal line here, or horizontal asymptote. So let's look at the first statement. F of x is negative and increasing from -3 to 0. All right, so -3, x is -3 is right here. 0 is right here. So you're looking at this piece of the function right here. If I read left to right, it is increasing. However, these values are not negative. These values are all above the x-axis. These y values are all positive. So this is incorrect for that statement. So I'm not going to choose A. The next statement says, as I approach negative infinity. So as I go left, as I go from right to left towards negative infinity, my y's are going down to negative infinity. Well, if I go to the left towards negative, my y's are going down, but they are not going to negative because of that horizontal asymptote. My y's, and I just caught this, the f of x, that equal sign should really be, that should be an arrow, not an equal sign. I'll fix that later. So this is saying, again, as x approaches negative, as I go to the left, my y's are approaching negative infinity. That is not true. My y's are approaching that asymptote, which has a value of y equals 2. So this right here should have been 2 to be a correct statement. So I'm not going to choose B. Next statement, the domain is all real numbers. That is true. That is true for every exponential for the reason I stated before. And also D is not true because the range of an exponential function is constrained by this horizontal asymptote here. All right, so the answer to this question is C. And we are done, guys. Good luck on your quiz.